Nonetheless, why don't we get started? All right, so where we last left off, we talked about the anatomy or architecture of a learner, and we talked about the representation of data as a vector-valued quantity so that we could plot them as points in some high-dimensional representational space, a so-called feature space. And as such, if we take every single data point, if we have n many data points, that results in n points in feature space, and those n many points in feature space in the literature are often called a point cloud. Now, if you have categorization of these various data points, and we're going to take the simplifying assumption that these data points are assigned to two different categories. In the categories we carried forward was the idea of the credit approval problem. Namely, you have two categories of customer, those who are approved for credit or mortgage based on his or her mortgage application information, and those who are not approved. Now, in this case, the data points that are colored green are those who are approved for credit, and the data points that are colored red are those who were denied a credit. And you can also, as numerically, describe this approval or denial with a +1 for the positive case, the so-called positive examples, those who were approved for credit, and the -1 cases, the red ones, those who were denied credit. And so if you look at the point cloud in feature space, you'll see that there's a natural grouping among them, these two groups, and we want or seek out to arrange them mathematically into some groups so that when we encounter a new input, a new customer as described by his or her set of attributes culled from the application, that the system would output a correct or sound or good decision should you approve this new person or not. And so where we last left off, we talked about this idea of a hypothesis set, which is a family of functions that you choose, you have control over it, and each point in this other yellow box represents the two settings for possible parameters that define a line. So we decide that we're going to choose a line, and we have the formula for a line, y equals mx plus b, and therefore every combination of parameters m and b, the slope and the y-intercept, is going to uniquely define a line. So we randomly select a line, and then we test this line against the ground truth assignment of +1, -1 approval denial decision for customers from the historical records at the bank. And if we find that it has a lot of errors, meaning it disagrees from this ground truth, then we seek out to search for another line. And so in a number of rounds, again and again and again, we keep searching for lines that best describe or best coincide with this ground truth labeling. Eventually, we will carve out a path through this set of possible lines, our hypothesis space, ultimately arriving at the end at some final best line or final best hypothesis. And so the ingredients that we needed for this learning model or this learning architecture, we first need data. And when you have that data, it's up to you to come up with a representation, some vectorized format of what form that data should take. And every instantiation of a vector, its set of values, are its features, and each individual or record will correspond to a certain set of features. Now, this relates back to what we talked about when we had the image examples, and we talked about color features and we talked about shape features. If you think about a vector of color and shape, the appearance-based representation associated with the building image and associated with the sunflower image, well, all of those sunflowers, imagine, you want to build a classifier that'll take an image and say, yes, this is a sunflower, or no, it's not a sunflower picture, right? So imagine if all of the green points were some vector representation of the color and shape of sunflowers, and then imagine also if the red points were some vector representation, color and shape features for the building, right? So if you plot all those out in feature space, and I'm just showing two here on the board just because that's all I can do on a 2D surface with the slides, but you can see that those buildings are more similar to one another, and therefore they're going to be closer to one another geometrically, their relative proximity in feature space. And those points representing sunflowers, they're going to be closer to each other. Yes, there will be variations about the color and shape of a sunflower, but the sunflower images, as described by their vectors, will be different from the building images. and that manifests in the geometry of the point clouds. You'll see that the green points are close to one another, but far away from the red points, which are close to other red points. Does that make sense? Any questions about this? I'm really tired because I have the coffee in my hand without even realizing I did that. Um, Let me put the cup down. All right. So we need a couple things in a learner. We need data and we need a representation, as we just talked about. We also need a hypothesis set. Now, that's an educated guess. And there are various strategies people use in machine learning to try to arrive on a hypothesis set. And one of the things we talk about in a semester-long grad level course in machine learning is what the impact is or the consequence is of your choice of hypothesis set. Now, certainly, you could choose a hypothesis set. We didn't have to choose lines on the plane. We could have chosen all degree 100 polynomials, right? That's a really big hypothesis set. Now, in the physics of learning, if you choose a hypothesis set that's really big, that corresponds to a function that can describe a lot of different geometries between two sets of points in point and feature space, point clouds and feature space. And that's a good thing because it means that you can separate points of one type from points of another type. But the consequence of that is if your hypothesis set is too descriptive, right? What it means is that you pay for that in needing more data. There's this trade-off. You can be very descriptive, but you need a lot more data. If you have too little data, you can only afford a certain amount of descriptiveness in your hypothesis set. And so in a semester-long course in machine learning, we talk about all the various trade-offs, the so-called physics of learning. If you push here, what happens over there, right? If you poke over there, what happens over here? So you need a hypothesis set, and that's of your choosing. Then you also need an algorithm that's going to search through that hypothesis set. And we noted this in this diagram as just being a sort of wandering path through the space of lines on the plane, right? Every single choice of M and B, every one of these dots as I've represented in this hypothesis set, every choice of M and B is a different line, a different slope, and a different y-intercept. And so if you're going to search, you can search. It's entirely up to you how you search through the hypothesis set. Now, again, if you completely randomize your search, there's a consequence for that. And that's another set of physics, if you will, properties in machine learning. It's going to take you a really long time to find the best hypothesis. Moreover, the path that you trace when you're searching for hypotheses in a hypothesis set, trying to find the final best hypothesis that most closely agrees with the ground truth labeling of +1, -1, green or red, however you choose to depict it, if that path is too jagged, i.e. not smooth, you're going to get poor solutions, right? And there are various reasons for that. Okay, so there are all these physics that we won't necessarily talk about here, but whether you want to be a machine learning practitioner or not, you're going to have to deal with data going forward, whether it's your primary responsibility in your career or not. Data is all around us. So you have an algorithm, you have a hypothesis set, and the algorithm's job is to search through the space of hypotheses, and both the hypothesis set and the algorithm are called the model, right? That's your learning model. And those two things are completely under your control. Everything else is not under your control, and certainly the representation you choose is also under your control, and there are various physics, if you will, properties associated with that. And so you also need this last part, an error measure or an error function. And that error function's job is to report or to quantify for you how far off you are from the ground truth labeling, because it's that error function that's going to drive the search. Okay? Any questions about this? No? All right. So let's continue on. And so this completes our anatomy of a learner. And with that, we can now do all sorts of things in building automated systems. Okay, so let's take a look at some learning model examples. Now, the model corresponds to, as we said, the hypothesis set, which is the type of function, and the search algorithm, the way you search through those families of functions. And so neural networks, right? Well, neural networks are a type of function. You represent them graphically, and they're nothing more than weighted sums that are composed with functions of other weighted sums. Now, As of late, there's been a renaissance in neural networks, so-called deep networks, deep learning networks. And a deep learning network is nothing more than a neural network that has very many layers. It's deep, so to speak. And there have also been some advances in high performance computing, specifically GPU and other learning runtimes called TensorFlow. A tensor is a generalization of a matrix. A zero-dimensional tensor is a scalar. One-dimensional tensor is a vector. Two-dimensional tensor is a matrix. Three-dimensional tensor, you can imagine, is a cube that has values in every location of the 3D array, and so forth. And TensorFlow is a very cleverly written library that allows you to multiply effectively matrices and vectors together and take those partial results and propagate them to another computation. And when you're learning in a neural network, you need to multiply a lot of vectors and matrices together and propagate those results to another set of operations. And so neural networks in deep learning is a type of function, and backpropagation is the algorithm that you use to search through the set of weight vectors that collectively define the parameters that govern those particular categories of functions, the neural network functions. Okay. There's also decision trees. A decision tree is another type of classification model, and a decision tree works off of the concept of a split. You have your sample data points, and each data point has features, and you're basically testing each feature of each data point to see if its value for that feature is less than or greater than a certain value, right? So then those that pass the test, you group them together. Those that fail the test, you group those together, and then you successfully run that iteration again until you end up with subgroups that all have the same labels. And so decision tree is a category of function. It's a bunch of successive tests of value. And the method you use to search through those different tests of value is called gain ratio splitting. You're looking at the reduction in entropy in the labels associated with the resulting subgroups. And then, and I won't talk about all of these, multi-frontier optimization. The search method is genetic algorithms. When we talk about regression, that's a predictor that predicts real valued quantities. Stochastic gradient and pseudo-inverse are the ways of searching. Pseudo-inverse is how you invert a matrix. It's a method for doing that. Stochastic gradient is a randomized way of searching through a set of weights specific to regression, logistic regression to be in particular. Then Bayesian networks is a probabilistic model. Belief propagation is a way that you search through the set of probabilities that most closely coincide with the data that you're seeing. And then lastly, Markov chain Monte Carlo is an approach for systems that change in time, and it's depicted as a probabilistic graph, and Metropolis Hastings algorithm is the way you search through the space of those functions. And so every model has a hypothesis set, a type of set of functions, and a way that you search through those set of functions. And you also have an error function that tells you whether or not the particular version of the function you're dealing with while you're searching, how closely it coincides with these ground truth labels from your historical data. Does that make sense? Okay. I really wish I could put together an undergrad version of a machine learning course. We have a grad version that first-year master's students take in the spring semester. Okay. So let's take a look at learning categories. There are two major flavors, or really three. They're variations on the two major flavors, but there are two different categories of learning. One is so-called supervised learning. Now, with supervised learning, you have the vector-valued input descriptor for your data, your historical data, and then you are provided with a label. That label is the ground truth category to which that particular instantiation of data belongs. And so in the case of the credit classification problem, we have a customer record, which would have things like years in residence and annual salary as the descriptors if it were a two vector. And then you have a label +1 if this person were approved for credit, or -1, excuse me, -1 or -1 if this person were denied credit. And so at the end of the day, what you're trying to do is find some weighted combination or some function of the input features that are predictive or that add up, if you will, to that +1 or -1 label. And so with so-called supervised learning, you're given the answer. And what your function you're searching for is one that knows how to produce those answers as a function of the inputs. Does that make sense? And so one of the examples is coin classification. So let's say you have a bunch of coins, and this is an application I would love to do in a version of this class. Um, you can take a look at the size of a coin. You get a camera, and you have a coin drop down a chute. You make that chute transparent so that the coin aligns and drops down the slot in the chute as it falls into a receptacle because someone inserted it. And then you have a high-speed camera, snaps a picture. So that coin has a size, okay. It also has a mass. Well, you know the weight, or the mass, I should say more correctly, of all the coins that are in the receptacle. You drop a new coin in, you know the change in mass. So you know the mass of that particular coin. So you could absolutely compute two features, size and mass. Size being the number of pixels that coin occupies, and mass, and treat them as features. Now, certainly, not all coins, even for the same coin like a dime or a nickel or 25 cents, what have you, from one coin to the next, it's going to be slightly different, right? And so if you plotted them in feature space as points in two-dimensional coordinates where the horizontal axis is the size and the vertical axis is the mass, you're going to get different clouds, if you will, corresponding to the various denominations of coins. And so here, you know the 10-cent coins, you know they're 10 cents, so that's a ground truth label. You know that the penny is a 1 cent value, ground truth, so you have those labels. Likewise, for the nickel, it's 5, and for the quarter, it's 25. And so you see some natural groupings here. And so what you can do is you can take a bunch of lines, linear classifiers, and find a bunch of lines and let them vote with one another to ask the question, is this particular point, is it a 10-cent piece or not a 10-cent piece? Is it a 5-cent piece or not a 5-cent piece? Is it a 1-cent piece or not a 1-cent piece? And if you combine those things together and let them vote, you can actually get a classifier that when you train it and then use it on new data, i.e. new coins, it'll actually register on the machine. You just inserted 25 cents. Okay? All right, any questions about this? Does that make sense? And my pocket is buzzing. Somebody's on the plane. All right. They didn't need to do that. All right, when I'm teaching. Anyways, that's what mother-in-laws do. uh, she's a lovely woman. It's actually a fun trip, but just not while I'm teaching. But nonetheless, all right. So we have a bunch of coin values, and this is a so-called supervised learning problem because you have the ground truth answer, and now it's up to you when you run your learning algorithm, finding four different lines, three different lines, I should say, that vote. It's now about how do you choose a line that is a good descriptor for what that given answer is, whether it's 25, 5, 10, or 1. Does that make sense? Okay, any questions? So after the break, you're actually going to have an assignment to actually do learning on the credit classification problem. Okay. So there's another flavor of learning or type of learning called unsupervised learning. Now, supervised learning, you have the answer. Unsupervised learning, you don't have the answer. And unsupervised learning looks like this. So let's imagine you have the same set of coins as your training data. Now, you can measure the features of these, the size and the mass, and you plot them. In the previous slide, for the point cloud for the coins, we knew what the answer was. We knew this grouping was the 25-cent pieces, that grouping was the 5-cent pieces, 1 cent, and 10 cents, right? But in the following slide, for the unsupervised learning case, you're not given the answer. You just have a point cloud, and you don't know what is what. You only have their position in space in some geometry, some relative relationship to one another. So what do you do with unsupervised learning? If you don't have the answer, the most you can do is make comparisons between these points in feature space. So you start out and you say, you know what? I'm going to make the assumption that maybe there's one group, and you group them all together in one group, and then given that grouping, you measure the variance and standard deviation in the mean across that one group. And you say, you know what? That's pretty big. That's a pretty lousy grouping. I want my groupings to be relatively small and spaced apart. So you then say, okay, well, I'm going to assume there are two groups, and I'm going to measure the pairwise distances between these, and those that are closer together I'm going to put in one group, and those that are closer to one another I'm going to put in the other group. Things that are far away from one another I'm going to assume they're in different groups. And so now you're assigning them to different groups. And if you keep doing that for one group, two groups, three groups, four groups, and so forth, eventually you'll get a grouping that coincides, not necessarily 100%, but for the most part, almost completely correct relative to what the ground truth is. So you run that clustering, the association of inputs to groups based purely on their feature vectors, not on the answer because you don't have the answer. And that's called unsupervised because you don't have that answer. That answer is sometimes called your supervision, right? And that's clustering. It's the using of features, and specifically the distance between points in feature space, things like cosine distance and L2 norm. There are all sorts of other things, Minkowski distance, Mahalanobis distance. You could get a whole thesis at a master's level just on distance measures and their properties. So you group them together, and then after the fact, once you find a good grouping, you know it's a good grouping because their means and variances, the variances are relatively compact for each group. You go in after you're done with your grouping, and now you take a look at those individuals that are in each group. And then you say, aha, these are quarters. These are dimes. I'll call these nickels. Now, clustering is used quite frequently in supermarkets, right, for this custom couponing. And so people in different stages of life, they buy different things from the supermarket. Maybe if you're, living on campus or off campus and college student, you buy these fast convenience foods, things that are prepared meals, or you heat it up minimally, don't do as much processing to prepare these food items. Then, you start working in your careers and you buy something different. Then maybe if you have a family, and I know, when my daughter was born when she was an infant, we bought different things from now that she's 8 years old, right? So you know that there are young families, families with infants, families with teenagers. Maybe they buy more milk and other stuff like that. And so absolutely, customer purchasing behavior is unsupervised. You don't know what to call these customers, right? But certainly they can be arranged and put into groups based on their purchase behavior. So imagine then these axes were on the horizontal axis the number of gallons of milk or the number of quarts of milk that a family bought, that somebody purchased. And then maybe the vertical axis was something like the number of cups of rice that they purchased. And I'm just making up these axes. So then for each customer purchase, you know exactly what he or she bought. You could even have an axis in multiple dimensions where each axis represents the number of each type of product. So if that store had 1,000 different products, you'd have 1,000 axes. And if you bought two of those products, you would be at two tick marks on that particular axis for that product. And in that case, each point in that really, really high dimensional space would represent your market basket, the set of items that you purchased. And so when you go into these stores, they give you these saver cards, and those aren't to be nice. That's so that they can track your purchases over time. Because believe you me, they do lots and lots of data mining and categorization on this. So with the custom couponing, let's say you have two products. Maybe it's a particular brand of rice and then a particular brand of milk, and then each tick mark represents how many units or SKUs you purchase for each one of them. So now you have a bunch of customers. Some customers purchased a small number of SKUs for the first product and the second product, maybe a medium amount, twice as much, and maybe three times as much, right? So you have those dots, those point clouds in feature space representing the purchasing behavior of customers. So now you run clustering, you group them together based on distance, and let's say you get three groups. You go back in and you say, okay, group A, I'm going to call the parents with grown children. Group B, I'm going to call that the parents with teenagers. And maybe that last group I'm going to call, after I go back in and look, I'll call that the parents with young children, right? The families with young children. So then what you do, some new person comes in and makes a purchase. Well, what do? You describe that person in terms of the number of units of each product, and then you plot that dot and you see, oh, which cluster does this dot fall into, right? You have the mean of each cluster, you have the variance of each cluster and can compute standard deviation, so you can absolutely determine, this new person who purchased, they fell into the second group, so I'm going to call them a family that has teenagers. So now you know what they purchased. You also know what people in that group tend to purchase. Because this point has a projection along each axis, you can also say, people who buy this type of amount of that product also buy a certain amount of another type of product, as well as other products. So then what do? You check your inventory and you say, gosh, well, what is not selling very well? Oh, okay, it belongs to that grouping. So let me print out a coupon for it, take off 50 cents, print it out at the kiosk, and try to encourage that person who just purchased because their behavior looks a lot like the purchases that this group makes. Maybe I can get them to purchase that other thing because there's a coupon. Does that make sense? And so companies use this all the time for custom couponing, for recommendations, right? You browse stuff on Amazon. People who buy, say, an Xbox controller might want to, at some point in the future, buy a wireless networking card for it, or networking adapter. So again, they look at the behavior, and then those recommendations are just randomly chosen items that people in that grouping also tend to buy, right? And so companies make a lot of money off of just clustering. And you could spend a fantastic career doing clustering, and you'll be spending a lot of time coming up with the feature representation for that data. And so you don't need to believe me, and I hope you try for internships on this stuff. Look at corporate offices. And when I say corporate, I don't mean the individual retail stores. I mean the corporate offices where they do the research and development. Look at corporate Walmart, corporate Target, corporate CVS, Walgreens, all of those. They all do this. Okay? So I hope you do consider that. You could literally make a whole career just off of clustering. Okay? All right, any questions about this? Does that make sense? Okay, so that's unsupervised learning. And there are also hybrids. There's something called semi-supervised learning. Semi-supervised learning is often used with tagging images. And what semi-supervised learning is, it's a hybrid between supervised and unsupervised. Supervised, we said, has labels. You get the answer. Unsupervised does not have labels. And so what semi-supervised is you have a small number of examples that you have labels for, high quality labels that are correct. And you have a large amount of data. And the question is, how do you use those labels, those answers for that small amount of data and apply it to the large amount of data? And sometimes that's called label propagation. And so you can imagine for this version of the point cloud where there are no labels, if you had one or two quarters that were somewhere nestled within that top grouping, and then you had one or two nickels that were somehow nestled within the other grouping. So then you have a small number of high quality labels, and then that's the supervised part. But the semi talks about then you take those high quality label things and you push or propagate its label to those examples, those points that are nearby from the distance measurement standpoint, right? So you can almost imagine this label is diffusing out around it in space. So those points that are unlabeled, that are similar, are going to be close by, and therefore they're going to assume the label of something that has a label. And that's called semi-supervised learning. And that's used often. Let's say you're on the web, you do a Google search on the Google image search, and somebody has pictures of dog, and on their web page, and they said, "Hey, take a look at my silly dog." You know, there's the picture, and there's the word dog. So that must refer to that picture. That's a picture of a dog. That's a high quality label. So now you have maybe 100 other images that might look like that particular dog, but they don't have a label. You use the fact that your labeled picture resembles or is close by in feature space to those unlabeled ones, and you just say, that must be a dog too. Does that make sense? Okay. Any questions about this? So we have supervised learning, unsupervised learning, and that hybrid semi-supervised learning. So with that, we'll end the module, and then we'll spend a little bit of time in this next one And after that, we'll pick back up after the break with some specific implementation guidance. So, any questions? So today I'm going to focus on the algorithm. And again, this is from that same URL associated with a machine learning course from Caltech. It's very well done. We talked about the credit approval system. You input a representation in vector representation of all of the information from a record of a credit applicant. Now, we've been only talking about years in residence and annual salary, but there's lots of other stuff that collectively describe a credit applicant. I'm simplifying it in terms of two features just for the sake of discussion. So we have this feature vector representing a single applicant. Each applicant has its own set of data and therefore is represented as its own feature vector instance. We run it through this credit approval system and it outputs approve or deny. So we talked about all the components. We have this theoretical concept, the unknown target function, and it is responsible for assigning these approval denial outputs or labels associated with the historical records. You have no control over it. You don't know what it is, but it's out there merrily doing its work. The good news is it's telling you what it would do given a certain credit applicant. Oh, this one, I'm going to approve that one. Oh, the next one, that one, I'm going to deny that one. Oh, the next one, I'm going to approve that one. And so the idea then is using your hypothesis set that you have control over, and you make an educated guess about what type of function is a good function, and you're searching through that hypothesis set with your learning algorithm to find one that very closely mimics the approval, denial, or plus one, minus one labels from the target function. And so we talked about feature space representation. In this particular example, we have two features for the credit problem. We talked about salary, which is on the horizontal axis, years in residence, which is on the vertical axis. So here we have someone who makes 70,000 and has been in residence for 7.5 years. Next, we talked about having a set of points in feature space that represent all of your historical records. Some of them are approvals, the plus one labels, or the green colored points. Some are denials, which are minus one labels, or the red colored points. And so now we choose our hypothesis. In this case, it's a line in the plane, which is parameterized by two things, slope m and y-intercept b. And so we need two real valued quantities, and we're going to search through those parameters all possible values for some line on the plane that best coincides with the ground truth labels. Now, when we say coincides with the ground truth labels, you can imagine this line as separating the red points from the blue points. And so we want some line such that the green points are going to be on the positive side of the line, and the red points, for example, are going to be on the negative side of the line. Okay, any questions about that? All right. So, and there's that line, right? That's what I mean by mimicking the target function. So if you get a new customer that comes in, that new customer, you take his or her features from his or her credit application, and then you plot that point, and then you ask the question, is it above the line or below the line, once you find this final best line. And if it's above the line, you say, aha, that should be someone who's approved. If it's below the line, you say, no, that should be someone who is denied. Okay, so the architecture, we talked about the anatomy of a learner, and the red were those parts that you have no control over, but you still need to understand what their role is. And the black are things that you do have control over, namely the hypothesis set, learning algorithm, and the error measure. And so we focused last time on the hypothesis set. Our focus for this module is going to be on the learning algorithm. And in particular, I'm going to show you something called the perceptron learning algorithm, or PLA, how it works mathematically. But to do that, we have to then develop a little bit of rigorous description of how we define the line. Now, before I said y equals mx plus b, where m and b are the parameters of the line. That's absolutely true. But in order to mechanize the search, we need to do a little bit of fix-up to this, because we also need a way of measuring this idea of above the line or below the line. Okay? All right. Any questions about this? All right. Let me do a time check. 10:05. So let's take a look at the model, the function part itself. We talked about the line being parameterized by m and b, the slope and y-intercept. That's absolutely true. Now, mathematically, rather than using m and b, it's a little bit wonky because you want to define things as a vector, right? So rather than saying m and b, we're going to say w1 and w2. W1 is the first weight, W2 is the second weight. It's still slope and y-intercept, but now, we're now going to say W1 and W2. Okay? All right. So now a line in the plane has two weights, W1 and W2. If we had 3 points, let's say if we're in 3 dimensions instead of salary and years in residence, what if we had salary, years in residence, and years of education is another thing they ask on mortgage applications. So if we had 3 dimensions, instead of W1 and W2, we'd say W1, W2, and W3, right? That's why we go to W1 and W2 instead of M and B, because eventually you'd run out of letters of the alphabet, right? So you have a weight associated with each dimension, right? Here it's a line in the plane. We have W1, W2. If we're 3 dimensions, we'd have W1, W2, and W3. So if you have an arbitrary number of dimensions, and this is akin to going to the supermarket example. If you had 1,000 different items for sale in the supermarket, well, each point would be a point in 1,000 dimensions, right? So if you're going to define a line in that 1,000-dimensional space, we now change the notation or the nomenclature. So this is a so-called linear model. It's a linear model because the weights are going to be used to compute a linear sum of all the features associated with each data point. And so you call it a line when it's in a two-dimensional space. If it's 3 dimensions, you call it a surface. It looks like a sheet of paper. And that sheet of paper is rigid, right? It's a plane, and it can be oriented in any arbitrary orientation. Beyond 3 dimensions, that linear model is called a hyperplane, right? And you can imagine a generalization of this sheet of paper in 1,000 dimensions. It's called a hyperplane. And so now we'll say hyperplane in general, and we'll use that as a synonym for a line. A line is nothing more than a hyperplane in 2 dimensions. Does that make sense? Any questions about this? Okay. So we have a weight, because it's a linear model, associated with each dimension, where each dimension measures one of the d-many features associated with your data point in your vector-based representation. Okay? So now you can imagine for an image, if you had 30 bins representing the color and 10 bins representing the edge orientation for an image, that'd be a total of 40 bins, so you'd have a 40-dimensional representation. Each dot in 40 dimensions would represent a particular image. Does that make sense? Okay, and we'll get a chance after the break to play with this to really drive this home. Okay, so we have this d-dimensional problem, and we have each feature, x1, up through and including xd. Now, this x on the left-hand side of equality, that should be in bold. That represents the x vector, right? But the x1 through xd in this parenthesized expression, that's a d tuple, and the order matters. And each one of these x's with the subscript, x1 through xd, those are the features. Or you could call it the coordinates in this d-dimensional space. And each one of these coordinates is a computed feature, the same way we talked about the bins of the color histogram and the bins of the edge orientation histogram, right? So we have the attributes or features describing a customer, and then our linear model, our hyperplane, you're going to have weights, one weight for each one of the features. So if you have a d-dimensional input vector, you also have a d-dimensional weight vector. In similar fashion, in the previous slide, 2 slides ago, or 1 slide ago, we have a 2-dimensional vector or representation, and therefore we have a 2-dimensional linear model, which is M and B, or W1 and W2. Okay? All right. Any questions about this? Does that make sense? All right. So now we're going to introduce this notion of a score. And the score is going to be a number, scalar, and we're going to call that T. And T is going to be a threshold, and that threshold T is such that if we compute the weighted sum of the terms in our W vector and the terms of our feature vector, X, we compute a weighted sum. If that weighted sum is greater than that threshold, then that means you're a safe risk and you get credit. If your weighted sum is less than that threshold, then you're considered a denial. You're a bad credit risk. And so everything that's an approve, we're going to call +1 or +1. Everything that's a denial, we're going to call -1, right? And so our weighted sum is you have some customer, you have your current version of your hypothesis that you've selected, and you calculate x1 times w1 plus x2 times w2 plus x3 times w3 up through and included plus xd times wd. So literally, you multiply each weight in our linear model, our hypothesis, with each feature from this customer vector. Does that make sense? Any questions about this? Okay, so let's take a look at this mathematically. We have our threshold, and we said if the weighted sum is greater than the threshold, you approve for credit. So how do we do that mathematically? Okay, well, we start at W1, we end at WD. We start at X1, we end at XD. So we say W1 times X1 plus W2 times X2. So in our summation, we take the sum. For I goes from 1 to D, to that dimensionality, and we're going to sum up each W, W1, W2, W3, with each feature, X1, X2, X3. So we compute that sum, and we test to see if it's greater than T, our threshold. If it's greater than T, then we say, okay, approve for credit. If it's less than T, we say, okay, deny this credit applicant. Okay, does that make sense? Any questions about this? No? All right. So that's going to be our scheme, but we have a little bit of a problem here. This is kind of weird to program in MATLAB or Python or what have you. So we need some sort of closed form expression, some function that we can actually code, because you don't want to have a function that says, okay, compute the weighted sum. Okay, we can do that in a vector, W transpose X. We can, but how do you check if it's greater than, less than? That's a little bit weird because you have to have an if statement and stuff in your code. So let's come up with a mathematical expression that we can implement easily as a function. So you can rewrite this, and let me do that out on the board. All right. So we just said the sum I goes from 1 to D of Wi xi is greater than threshold T. Okay. Well, this is an expression. We have our inequality greater than, and we have T on the right-hand side of this inequality. So what can we do? We can subtract T from both sides of this inequality. If we do that, we have the sum. I goes from 1 to D, Wi xi minus T is greater than 0. So now we have an expression that says, is this quantity, the weighted sum minus the threshold, is it positive? Is it greater than 0? Now, there just happens to be a function, and this is also in MATLAB as well as in mathematics, called sign, S-I-G-N. That is not the same as sine, S-I-N, which is the trigonometric function. Sine is a function where if you give it a parameter, if that parameter is positive, sine will return a +1. If that parameter is negative, sine will give you a response of -1. Does that make sense? And literally in MATLAB, SIGN, parentheses, you give it a parameter, right? And we'll tinker with that after the break. So here, now we have that weighted sum minus T. Is that quantity positive or negative? So we use that as the parameter to sign. And now this becomes our function, which we'll call h of x, the current working hypothesis operating on that data point vector x. Does that make sense? Any questions about this? Okay. So h of x will output one of two quantities. If you give it a customer record expressed as a vector, it'll output a +1. That means it's approved. That's a positive example. If you give it an input vector whose result is -1, h of x, and that's h of x definition, it'll give you a -1, which means to deny. Okay? All right. So that's going to be our mathematical approach we're going to use with our algorithm. Let's look at the way we do search. Okay. So this is our score here. This is our h of x, and h of x is unique depending on your setting of w. If we have a particular setting of w, that's w1 through wd, let's say it's all ones, for example, that's one particular hypothesis. If we change w, say, to all twos, that's a different hypothesis. So each h of x is different depending on that setting of w. In the same way, each line was different when we talked about a line in the plane based on a unique selection of m and b, the slope and the y-intercept. So it's the same thing, only in more than two dimensions. Does that make sense? Okay, any questions? All right, so more coffee. It's like when you step and you feel the floor still moving because you haven't slept enough. Okay, and so let's assume that our point cloud, that it's so-called linearly separable, meaning that you can separate all of the plus points, those approvals, from all of the minus points, vectors, the denials, using a straight line. If they're linearly separable, then that means a linear model is a good choice of hypothesis. Now, of course, there's some other things that you can do if it's not linearly separable. That's beyond the scope of data analytics, but there are all sorts of things you can do, and we spend at the graduate level 2 semesters talking about all those things. But let's just assume and just take it on faith at this juncture that you can separate the data points somehow with a linear model, and that property is called linearly separable. Okay, so we're going to clean up this expression because this h of x, it's still a little bit too clunky to implement in something like MATLAB, Python, Java, and so forth. Absolutely, you could implement this, but for convenience, if you want to make this fast and you want to make it something you can implement very compactly, maybe put it in an embedded system, mobile device, and so forth, you want to make it more mathematically convenient. So let's do that in a number of steps. So this minus t, that minus t is kind of weird, right? So we're going to replace this minus t with a quantity we're going to call w naught or w0, right? It's just a mathematical convenience. So we're going to replace minus t with a w0, and then we're also going to add in a new variable. We're going to call that x naught, x0. And x0 is going to be fixed to a constant value of 1, right? And I'll show you exactly why in a moment. So now, if we replace that minus t with w naught, we get the following expression that's on the board. We have the weighted sum, the sum of wi xi, I goes from 1 to d, plus w naught, because that's our replacement for minus t. So you see up there in the upper right, we have minus t. We're just replacing it with a plus w naught. And it doesn't matter, w naught could be positive or negative, right? So we can absolutely change that minus t to a variable w naught, because we didn't set any restriction on what w naught is. So I'm going to write out h of x is equal to sine, and we have our weighted sum, I goes from 1 to d, wi xi, plus w naught. Okay. Now, a property of numbers, right, there's something called multiplicative identity, which is 1, right? If I multiply 1 times anything, it doesn't change the value. That's w naught. It doesn't matter what w naught is. It could be a fraction, it could be an exponent, it could be positive, negative. Its value does not change if I multiply by 1. So I just got done saying I'm going to include this variable x naught, but its value is going to be fixed to 1, right? So if I say 1 is the same as saying x naught, so x naught literally in my code, I'd say x naught equals 1, right? I now replace this w naught, which was a replacement for minus t, with 1 times w naught, which doesn't change its value. And I'm calling x naught as being this dummy variable that's fixed to 1. So I say x naught times w naught. So now this expression for h of x is sine of my weighted sum. I goes from 1 to d, wi xi. That hasn't changed. And now I say plus x naught w naught. Okay. So maybe you can see what I'm trying to do here. So now you notice I have d many terms here, wi xi. I also have a w naught times x naught. So now what I'm going to do, I'm going to roll this term here, the addition of this term, into the summation. And when I do so, I can write it compactly by changing the index to 0, change that to D, and say WI XI, right? So I can sum together the first D terms in the weighted sum, and then add this to it. Or I make the observation that, wait a minute, I have X in a subscript, I have W in a subscript. I'm just going to fold that in to the summation and have my index change accordingly. Does that make sense? Okay, so I do that, and now I write that step of replacing minus t with W naught. That's going to be my new version of the threshold. I multiply it by a dummy variable x naught, whose value is fixed to 1. It does not change the value of that W naught term. And now I modify my summation, and now I have D plus 1 terms. I have the 0th term, first term, second term, so forth. So this was D terms in the weighted sum. I'm adding another term to it, that 0th term. Now I have D plus 1 terms. Now the reason I did that is that I can make an observation again, that I can do this operation, that summation where I goes from 0 to D of Wi xi. I can make another observation that if I have W, and let's say W is a vector, and that vector has W0, W1 up through WD, and if I have X vector, and let's say that vector goes from X0, X1 up to including XD, if I take my W vector and compute the transpose, that now becomes a row vector, W0, W1, WD. And if I multiply that times my X vector, X0, X1, XD, when I look at the rules of matrix vector multiplication, if I take the transpose of W, this now flips it to a row vector. And now I take this across and that down, and I multiply like terms, W0 times X0, W1 times X1. So now, with this addition of W, or this change involving W naught and X naught, I can now compute this entire quantity, this weighted sum, I goes from 0 to D of Wi xi, as just the multiplication of two vectors. And I can do that in one line in MATLAB, and I can do that very quickly computationally. Does that make sense? Okay, so we do that, and now this computation just becomes sine, which is the sine function, is it positive or negative, of this W transpose, which is the weight vector augmented with a W naught, W transpose times X, where X is augmented, the original input feature vector, augmented with the X naught, which is fixed to 1. Does that make sense? Okay, any questions about this? All right, so now this is what we're going to use in closed form for our current working hypothesis. Now you notice here, for a given setting of W, it's a different hypothesis. If I change W, we're now looking at another hypothesis. Okay, any questions about this? Does that make sense? Now, remember when I first learned this, I was like, no, you're lying, right? And then you realize it works, and I'm like, oh my gosh, that's pretty crazy. So this is our form of our hypothesis. And now, to search, we're going to do something called PLA, Perceptron Learning Algorithm. And we said that if you change W, you're considering a different hypothesis. So now we need a way of updating or changing W. And this PLA update rule says, I want to change W such that I can correct for some point where the hypothesis disagrees from the ground truth label. So that means for some data point X, whether it's X1, X2, X3, X4, Xn, big N, the ground truth has said +1, approve, but h of x, when you run it on the x, it said deny, right? So that's an error. That's a classification error. And this is our error measure. So you take the number of errors your current version of the hypothesis makes, and then you pick some point on which it made an error. You look where it disagrees with the ground truth labeling, and then you do the following update. You say the new version of W, that's your augmented W, is equal to the current version of W plus whatever the ground truth label is times the value of that offending data point. And what that ends up doing is it ends up choosing a different hypothesis such that the misclassified data point is now correct from the perspective of the hypothesis. Does that make sense? All right. And so this is called the perceptron learning update. And this is demonstrated for two different cases of disagreement. Now, when you say W transpose X, that's also called the inner product. And the inner product is similar to the dot product. It's the projection of one vector on another vector. And so if a vector points in the exact same direction as another vector, they're right on top of one another, the inner product is going to be large. If the vector is pointing in the opposite direction, that inner product is going to be negative value, right? So here we have an example. The ground truth label is +1. That means this customer was approved. And so the X vector, data point, is drawn as this black vector here for the frame on the left, your left. And the W vector is here, this red. So if you took W transpose X, well, we know X's ground truth label is +1, but W transpose X, we project this black vector down to where this X vector goes. You can imagine drawing that ray completely left to right diagonally. If you project it down, it's on the minus side of that X vector. So sine of W transpose X is going to be negative. So that means H of X for this X is going to say the output is -1, but ground truth, the Y value is +1. So what do? You say, okay, the new version of W is going to be the old version of W plus Y times X. Well, how do you do that? You basically take this X vector and you add it to the tip of that W vector. And if you draw a new vector to the end of that, that's now your updated version of W. So you take this updated version of W, W plus the label, the ground truth label times X, and if you do W transpose of this, so this quantity transpose X, the projection is now positive. It's corrected for that misclassified point. And so you keep doing that again and again and again and again, and eventually you'll find a line that is very close to being correct for all the data points. It will be absolutely correct for all the data points if the geometry of the data is such that it's so-called linearly separable. You can find some line that separates the two groups from one another directly. Does that make sense? All right. Any questions about this? So please try this example and look through the video. The instructor who wrote the book that I take this from has won the Feynman Awards. Very excellent instructor. Has won a lot of awards. Okay, so please go through this example and through the video before the break, and we will pick up after the break with some MATLAB examples. So what is this actually doing? In a series of rounds, you keep doing this update. You find the new W using this update by choosing a misclassified point. You do the update, and then you reclassify all the data points using this new version of H of X. And then you choose a newly misclassified point, and then you keep doing that, the update again and again and again after rerunning H of X on all the points. You choose a misclassified point, and then you run the update again. So what ends up happening when you do this, W gets W plus Yi Xi, where Yi is the ground truth label for vector Xi for the custom record. If this is my Xi, and its ground truth category was +1, and H of X said it was a -1, that means this is the H of X. You did W transpose X, sine of W transpose X, and it returned back -1. So when you do this update, what it's doing is literally choosing a new H of X that goes past this point that was misclassified, so now it's classified correctly. And you keep doing that again and again and again, and the straight line would just basically go like that. All right? Okay, any questions about it? Does that make sense? Now, when you see it in MATLAB, this is the math, and you see it in MATLAB, the coding, I'll try as much as possible to have the coding mimic what's in the slides. Okay? All right. Any questions? Does that make sense? Yeah? All right. So that's it. Yeah, really? Well, there are a couple considerations, and that really is it, right? Something that simple works well. But with this simple approach And in a machine learning course, you find out that this seemingly very simple model can do a lot just by making very small tweaks here and there. And we talk about that in machine learning. But nonetheless, one of the questions, how many rounds? How many times do you run this update and this reclassification with the new version of h of x? How many rounds do you go before you stop? That's very interesting. Will it stop? Or will it, in pursuing correcting a misclassified points label, will it damage something that was previously correct? That's very interesting. Will this work for any sort of problem? You can get it to work for a lot of problems with, again, a little bit of tweaking using something called phi functions, transformation on the data. And so this straight line, the data is guaranteed to work if the data are linearly separable. If they're not linearly separable, you can actually transform the geometry of the data through something called a phi function and then use a straight line. And there are all sorts of properties and techniques associated with that. How do you choose the hypothesis set? Because there are consequences for choosing the hypothesis set. If you choose wrong, you can get very poor performance on new examples. If you choose right, you can get good performance. But if you're too modest, you can get absolutely horrendous performance. How do you choose the learning algorithm? Now, this learning algorithm, it can be iterative, it can be randomized. You can have it with certain properties, this idea of how you measure the coincidence between the ground truth target function and a particular working hypothesis. If you choose that function such that it's differentiable, now you can solve it in closed form and have all sorts of desirable properties with your algorithm. So how do you choose this algorithm? How much data do you need? Right? Because there are consequences for having a really descriptive hypothesis set. You need more data. Well, what happens if you don't have more data? Sometimes you can synthesize fake data by using a distribution and sampling. All sorts of considerations, and that's really the subject of machine learning course and pattern recognition. Okay? Any questions about this? Does that make sense? I'm sort of budgeting for more questions, so we can certainly end early. And that is all I had to say on the credit approval algorithm search. So with that, we'll end there. I don't want to get between you and spring break. I don't assign work over spring break. It's a personal thing from when I was an undergrad. When you do go on spring break, if you go away, please travel safely and travel back safely because we want you back here intact.